Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
We are diving deep today
Mm.
into what I'd call the secret sauce of profitable product development. This isn't just about building cool things. It's about hard economics and really engineering profitability.
That's the core mission right there. We're trying to uncover the critical strategies engineers use to make sure a product is efficient, high quality, and maybe most importantly, profitable before the first one even rolls off the line.
Mhm.
And the sources you sent show that in this world of, high-speed technology churn, the pressure is just immense. But the real leverage, the key to scaling and even just catching up is all in the upfront technology and design.
Exactly. The foundational challenge for any manufacturing company is turning, well, raw, low-value material into a finished, sellable product with the most efficiency and the least economic waste.
And some companies don't even know their true cost until it's too late.
Way too late. We're talking about companies that don't know the true unit manufacturing cost until well after production has started. So this deep dive is about preventing that catastrophic failure. And we do that by focusing on three pillars that are all connected: designing aggressively for cost, standardizing all your information, and then finally optimizing the production flow itself.
Okay, let's unpack that triad, starting where the rubber meets the road. Design for manufacturing and assembly, or DFM&A. This is where the cost constraints really come in.
DFM&A is the strategic cornerstone. It's a technique used to proactively to get ahead of the cost problem by simplifying the design into its components
Yeah.
and making sure the materials, the fabrication processes, that they're all aligned from day one.
So it's a total rejection of that old siloed model.
Completely. The old engineering designs it and manufacturing has to just figure out how to make it. That's gone. That model is a recipe for failure.
And when you look across all the principles of DFM&A, the single biggest takeaway seems to be simplicity. The main goal for the design team is to just reduce the number of individual parts.
Reducing the part count is, I would argue, the biggest lever you have. Every single part you eliminate takes with it not just its own material cost, but a huge amount of complexity and overhead.
Right. It's a ripple effect.
A massive one. Fewer assembly steps, less inventory to track, reduced logistics, and critically, fewer opportunities for defects. Simpler design just inherently means higher quality.
But to enforce that kind of discipline, you have to give the team a metric they can't ignore. This brings us to the mandatory cost goal, the unit manufacturing cost target, or UMC.
And that UMC has to be fixed on day one. The whole team has to be held strictly accountable to hit that number.
Yeah.
No excuses.
And the UMC isn't just some vague number. The calculation is really specific. It's what? UMC equals burdened assembly labor plus material costs plus tooling amortization, BL, MC, and TA.
That's it. And if you miss any of those elements, the target becomes worthless. It's not just the cost of raw inputs.
Let's dig into that material cost MC, because in almost every case, that's the biggest expense in the whole UMC calculation, right?
It is. BL is your wages, benefits, overhead. TA is, molds and tools divided by the product's life volume. But MC, that's where companies get hammered.
Okay, so what has to be included?
Well, it has to include the cost of the transformed material, the packaging for the piece parts, and this is critical, all the adders.
Adders.
Yeah. Adders include DIP, that's duty, freight, and insurance, plus the material acquisition cost, or MAT-ACU. The engineering team has to factor these in from the start.
I see. So if they design a component and the raw material comes from overseas, underestimating that DIP expense could just blow up the whole model.
Instantly. A small percentage miss on a high-volume product is a disaster for profitability. So you have to move that full, complete material cost estimate way upstream before the design is ever finalized.
Okay, that makes sense. It prevents that downstream sticker shock. But it does raise a question. If the UMC target is so rigid, what stops engineers from just using the cheapest, lowest quality materials they can find just to hit the number?
That's where the other DFM&A principles come in to support quality. The design rules themselves guide engineers toward efficient solutions, not just cheap ones.
Oh.
They apply basic DFA rules like designing parts with self-locating features to make assembly easier, or using self-fastening features like snap fits instead of adding a separate screw.
And making parts do more than one job.
Exactly, increasing multifunctional parts. A single component doing the job of two. And maybe most important, eliminating assembly adjustments entirely. Those are major failure points.
So DFM&A sets the goal of simplicity and it provides the design rules. But to achieve that, you need the second pillar. A standard, universal way to talk about every part, every material, and every process. That's classification systems.
You absolutely cannot manage what you can't describe consistently. The biggest production savings start with something called group technology, or GT.
And what's the philosophy there?
GT is the idea that you maximize efficiency when the design function is seamlessly integrated with materials, production, marketing, quality. Everyone. If you don't standardize how you identify parts, you just breed chronic problems.
Like what?
Excess scrap, rework, huge amounts of excess inventory.
Right.
All because you keep designing new parts that are basically identical to parts that already exist somewhere else in the company.
It's like a massive company-wide library system for hardware, and the core tool is the part family classification and coding system, which defines a part by its basic shape, not its function.
Precisely. The goal is to create a digital fingerprint for every single component. Usually, it's something like an 8-digit code covering basic shape, form features, size, precision, and material.
And that code isn't just for humans.
Not at all. It's used for generative process planning, where a computer can automatically figure out the best way to manufacture the part just by reading its code.
What's really fascinating is the logic behind building that code, this difference between E-trees and N-trees. Can you unpack that? It seems like a critical concept.
Yeah. Sure. E-trees are the foundation. They're hierarchical and mutually exclusive. They force you to make a choice that determines your path.
Okay, so an example would be,
Is the part rotational, like a shaft or a wheel? Or is it non-rotational, like a housing or a plate? You have to choose one. You can't be both. The other path is eliminated.
it's a hard-or decision.
Exactly. An N-tree, on the other hand, is non-mutually exclusive. It's for common attributes that can all exist on the same part. Special form features.
Like holes or threads.
Right. Does the part have a hole,
Uh-huh.
a thread, and a tab? You can select all three. An E-tree is like picking the primary color of car. It's red or blue. An N-tree is the options list. Sunroof, navigation, heated seats. You can have them all.
That analogy makes it so much clearer. And this same rigor applies to materials, right? You need an engineering materials taxonomy.
Oh, it's vital, especially now with all the environmental and cost pressures. Good classification lets engineers quickly search for materials based on things like energy requirements or recyclability. I mean, just knowing that recycled aluminum takes only about 10% of the energy of primary aluminum. They can drive massive cost savings and hit sustainability goals.
So we have the design goals from DFM&A and the data structure to support them with classification and GT. Now let's move to that final pillar, production planning. We've got the efficient design, the parts are codified. Now we have to actually make the thing and meet customer demand on time.
Right. And production planning is all about predictability, and that starts with forecasting. There are three main categories of methods here.
Okay.
First, you have qualitative techniques. These rely on expert opinion, consumer surveys, usually for brand new products or big policy decisions. Second is time series analysis, which just looks at historical data for trends and seasons.
And that third.
Those are causal methods. They're more mathematical, like regression analysis. They try to find a cause and effect relationship. For instance, how does advertising spend affect product demand?
Got it. So once you have that forecast, you have to manage the inventory to meet it. This is where materials requirements planning, or MRP, comes in, especially for what's called dependent demand.
Yes, MRP is a system that really separates the efficient manufacturers from the rest. See, for components in manufacturing, demand is often really irregular, very lumpy.
Right.
MRP converts the master schedule for the final product into a precise time phase schedule for every single component you need to build it.
So instead of just stocking 10,000 car door handles because you might need them.
Exactly. MRP lets you know you need exactly 1,000 on Tuesday, 2,500 on Friday, and 0 the next week. The big benefit is you can maintain a much, much lower average inventory. That's huge capital savings.
Okay, moving from inventory to the shop floor itself,
Mhm.
you have this challenge of job sequencing. You've got, say, 10 jobs to run on 3 machines. Deciding the order it gets exponentially complex.
It's computationally unfeasible to find the one perfect solution in a big shop. So practitioners rely on heuristic rules, which are basically educated shortcuts.
And a common one is shortest processing time, or SPT.
Right. In a single machine shop, it's one of the most robust. The rule is simple. Run the job that takes the least amount of time first.
Which feels a little counterintuitive.
It does, but it's mathematically proven to minimize both the mean flow time, how long a job sits in the shop, and the mean lateness. You're clearing out the queue faster.
And speaking of flow, that brings us to assembly line balancing. The goal here is just to assign work to stations to minimize idle time, right? The balance delay.
Exactly. And it gets incredibly complicated when you have mixed model assembly lines where you're building, say, 5 different kinds of vacuum cleaners on the same line. You're
Yeah.
not just balancing the work, you're constantly resequencing the models to prevent bottlenecks.
All these granular techniques seem to feed into bigger strategies like time-based competition or TBC.
They do. TBC is all about gaining an advantage by slashing lead times everywhere. Design, manufacturing, delivery, and it's very closely related to the Japanese philosophy, JIT, or just-in-time.
Which is really about waste.
JIT is the philosophical embodiment of eliminating waste. And waste here is defined very broadly. It's inventories, waiting times, scrap, equipment breakdowns, anything that doesn't add value. It's a holistic system that demands all the precision we've just been talking about.
This leads us perfectly into the final section, the actual physical tools you need to execute these plans. The goals of DFM&A, high-precision, multifunctional parts, they often require processes that traditional machining just can't handle. Let's start with plastics.
Plastics are notoriously difficult to machine well. The reason is they're poor heat conductors.
So the heat builds up in the tool.
Exactly. The heat from cutting can't dissipate through the material, so the tool gets extremely hot. This means you need super sharp carbide tools and special coolants to stop the plastic from melting or swelling, which would just ruin your accuracy.
And when traditional methods just won't work at all for super hard materials or really complex shapes, you turn to non-traditional machining.
That's when the tool chest gets really interesting. You have things like electrochemical deburring or ECD. It removes burrs using anodic dissolution. It's like controlled chemical erosion using an electrical current. Ultra precise, no mechanical stress.
Or just using raw energy.
Absolutely. Think of laser beam machining, LBM. You're literally melting and vaporizing material with a highly focused beam of light. Or thermally assisted machining, TAM, where you use a plasma arc to soften the workpiece just an instant before the cutting tool hits it.
These are the only ways to hit those demanding DFM&A tolerances sometimes.
For sure. Shifting to metal forming, there's a critical cold working process I want to highlight: peening. It's a key technique for preventing fatigue.
Peening. So you're basically hammering the surface of the part.
In a very controlled way, yes. It's often called shot peening. You're striking the surface repeatedly with tiny metal balls. This creates a thin surface layer that's under intense residual compressive stress.
And why is that compressive stress so important?
Because almost all mechanical failures in parts under cyclic load, think gear teeth, springs, are caused by fatigue. Fatigue starts with tiny surface cracks opening up under tensile stress.
Ah, so the compressive layer squeezes those cracks shut.
It effectively closes them before they can grow. You dramatically delay fatigue failure and ensure the part lasts its full design life. It's a huge payoff for a simple surface treatment.
Okay, finally, let's touch on mechanical fastening. Bolts over welding when you need to be able to repair something or adjust it.
Right. And for any high-strength connection, the key is what's called a friction-type connection. Use high-strength bolts, and you tighten them to an extremely high tensile stress. This creates a massive clamping force between the plates.
And that clamping force is what's doing the real work, protecting the bolt itself.
It is. That huge initial preload shields the bolt from the external cyclic loads, preventing the stress cycles that would otherwise lead to fatigue failure. It's an essential protective layer. But you have to get it right, because fasteners relax over time.
So if we step back and look at these three pillars, DFM&A, classification, and production planning, we see that profitability in manufacturing is, well, it's a perfectly connected loop.
It absolutely is. Aggressive design through DFM&A needs the organized information from classification and group technology. That rigorous data then enables effective planning through systems like MRP and JIT, and all that precision planning lets you use advanced manufacturing processes to their full potential. It's a closed system. Data drives design. Design drives execution.
And this is where it gets really interesting, I think. We move beyond the machines to the human element because these complex systems rely entirely on high-performance teams, engineering, manufacturing, purchasing, quality, all working together. The team success factors are just as important as the UMC.
And the research points to one surprisingly simple but profoundly impactful factor: co-location.
Just putting everyone in the same room.
Or at least in the same
Right.
facility. Having those multifunctional team members in a common space significantly improves communication, boosts morale, and ensures problems get caught early. And the reason is simple. It's the benefit of bumping into people.
The unplanned conversation in the hallway.
That's it. That organic interaction reminds someone of an issue or a design conflict that otherwise would have waited for a formal scheduled meeting, by which time it's already a bigger problem. It's the lubricant for the whole system.
That makes perfect sense. So as you, the listener, look at the immense complexity of setting up a coding system, the E-trees and N-trees for physical products, it raises a powerful question for all of us, no matter what our field is. What processes in your own work could be digital asset management, handling customer requests, internal docs, what could be made vastly more efficient, higher quality, and less costly if you just applied that same engineering rigor and standardized your own internal classification system today? Think about that framework of structure and discipline. Until next time, keep diving deep.